Hey physics peeps, we're going to take a look at solving conservation of energy problems, but these tend to be a little bit more complex. You'll start to see some patterns in here too of things that you have seen before, but stick with me and I want you to copy down these next two problems that I do, and then you're going to have two other problems that you will solve out yourself. And so doing these problems, can be a little bit tricky, but I think once you start to see it, it's not that bad. And it's really keeping track of types of energy and using the equations for energy, especially with kinetic energy, which is that 1/2 mass times velocity squared. Don't forget the squared. And then potential energy, where it is mass times gravity times height. Remember, for gravity, we use that number 9.8 meters per second squared. So let's take a look at this first example. It says a 58 kilogram basketball player that jumps off the ground at a speed of 4.65 meters per second. What is the maximum height she can jump above the ground? So they give you some of this information, and when I'm looking through this, they tell you kind of this little piece. Like, here's my mass. It's in kilograms. And then this 4.65 meters per second, that's a speed or a velocity. That's really all that they seem to give you. And then they're asking for what's the height that she can jump above the ground. This is dealing with energy because originally this basketball player, they're holding the basketball, and then they jump up into the air. You kind of think of this like a before and an after thing. And when she jumps up in the air to make a shot, off of the ground, we want to know how high that she's going to end up going. But like I said, this is dealing with energy because originally, just at the very beginning, she is starting to jump up in the air with a speed of 4.65 meters per second. Originally, she has kinetic energy because she is moving at this speed. We would say that she doesn't have potential energy because she is on the ground. Her height is 0. So we would say that all of her energy is kinetic energy. That's where drawing these little LOL diagrams is really helpful because we're going to keep track of what type of energy that they have. So I want you to draw this diagram for this problem. And originally, she has kinetic energy and 0 potential energy. Afterwards, though, she's going to go up in the air. And as she goes up in the air, her speed is actually going to slow down. So she's going to go up. She's going to slow down, slow down, slow down. And then she's going to come back down. But what this is asking is, what height does she get to at the very top of her path? If you remember, at the very top of her path, her velocity is 0, which means that her kinetic energy is 0. And now she has all potential energy. And so when we talk about this energy and transfer of energy, remember that total energy stays the same. And that's what these two ends represent, the before and the after. We can actually write out an equation for this each time when we solve conservation of energy problems. We know that our total energy, the kinetic and the potential energy, have to add up to equal the kinetic and the potential energy afterwards. So this is our rule. But in this situation, we can actually cross out some things. Like, we can know that before there's no potential energy, and we know that after there's no kinetic energy. So the kinetic energy and the potential energy, they're equal to each other. And now I'm going to put in down below the equations for these things, because up here they didn't tell me what the kinetic energy was. They didn't tell me what the potential energy was. I have to figure them out by using these equations. So for the kinetic energy, I have to use 1/2 times the mass of the player, and their mass is 58 kilograms, times their velocity squared, so the 4.65. But just be careful when you do this. Many people will leave it like this. Don't forget the square. Don't forget the square. So it's 4.65 squared. Equals, on this side, it's my potential energy. It's mass times gravity times height. So it's the player's mass, 58 kilograms, times gravity. We use that number 9.8 meters per second squared, times the height. And this is what we're really trying to figure out, because we don't know what height she has at the end of the problem. So we're just going to put it in h. So if you don't know what it is, you just leave the letter for it. And now I'm going to go through and do some simplifying and solve for that h. So I can take the 1/2 times 5.8 times 4.65. A lot of people find it a lot easier to work through that problem backwards and do the 4.65 first, because it's 4.65 times 4.65. And in place of the 1/2, you could put like 0.5 m times 58 times 0.5. So this is basically kind of what I plugged into my calculator. And I got 627.05 plus some other decimals, but that's okay. But then I can take 58 times 9.8. I get 568.4. But I have to leave in this h because that's what I'm trying to solve for. And now the last thing I need to do is solve for h. Right now it's being multiplied by this 568.4. I have to divide by 568.4 on both sides. Those go away, and I end up with 627.05 divided by 568.4. I end up with a string of decimals, and that's okay, but I get 1.10. Go out 2 decimals, you'll be good. But because I solved out for height, it's like a distance. We measure in meters. So this is my answer. So it's saying that if she starts off at this speed off of the ground, she will reach a height of about 1 meter off the ground, or 1.1 meters off the ground. So that's kind of that part. And when I solve out this next problem, and we're going to do something very similar. We have a 1.8 kilogram coconut falls from rest out of a tree from a height of 12 meters. Determine the coconut's speed on impact with the ground. When we're thinking through this problem, we want to think of things in terms of like before and after, like what we did before. And we want to play a picture in our head of what's going on. So like this coconut, it says that it falls from rest out of a tree. When we say before, it's before it falls out of the tree. So it's up here in the tree. And when we say after, this means after it falls out of the tree. It's saying determine the on impact with the ground. So it falls out of the tree and hits the ground. But just keep in mind, we're not thinking of like it hits the ground, lays on the ground, and you look at it and it's like, oh, it's not moving. Nope, that's not what we're talking about. We're talking about like as it impacts, what speed is it coming into the ground at? And so this is what we're going to end up looking for. But we can draw these LOL diagrams. And so I want you to copy down the L diagrams for these and then the work down below too. And so when we do this LOL diagram, we start with this coconut and it's up above the ground, so we know that it has potential energy. But be careful, some people would say it has kinetic energy because it's starting to fall, but remember that this one falls from rest, which means that it has no kinetic energy. All the energy is potential. Then, afterwards, when it's on the ground, here the height is 0. That means that there is no potential energy, but it has speed. And it's all kinetic energy. And when we write our rule, we know that the total energy, the kinetic energy and potential energy before something happens, it's equal to the kinetic energy and the potential energy after something happens. Total energy stays the same. But we can kind of make a little shortcut because we know that the kinetic energy here, that crosses out. The potential energy, that crosses out on this side because there's no potential energy here, there's no kinetic energy here. We just need to work with these equations. So we start using our other equations to fill in the information here. So remember, potential energy is that mass times gravity times height. So we use the mass of the coconut, this 1.8 kilograms, that's the mass, times gravity, it's 9.8. Oops. Times the height it is up in the tree, and that says that it was dropped from a height of 12 meters. So 12 meters equals the kinetic energy. Remember, that's the 1/2 times the mv squared. Don't forget the squared. So I could put in 0.5 if I wanted to for the 1/2 times the mass. Oh yeah, that was 1.8 times v squared. And v squared, it's not 0 here because we're looking at after, and as it's impacting the ground, it's the thing that we don't know and the thing that we're looking for. So we put in v in its place, but don't forget the square. The square has to fit in it. And so now I have all my information and I can go through and simplify my problem. So I simplify these numbers over here. They're all being multiplied, 1.8 times 9.8 times 12, and I get 211.68 on my calculator. And here I get 0.5 times 1.8, I get 0.9. But it's times v squared. My job is to get v squared by itself. First thing I need to do, divide each side by 0.9. 0.9s go away on this side. If I do this, I get 235.2 is equal to v, but don't forget the square. So we're not done yet though. Some people will get here and think that they're done. We didn't actually solve out for v. We solved for v squared, which means we have one more step. And so when we have to undo something, we have to do the opposite of it. And the opposite of squaring is a square root. So we undo squares by doing a square root on both sides. And if you take the square root of 235.2, you end up with velocity of 15.33 or 34 if you round up and go out 2 decimals. But this is our velocity. Because we solved out for velocity, our unit is meters per second. Big things that you need to take away from this. When you're setting out these equations, it's always EK plus EP equals EK plus EP. When you're solving for velocity, don't forget the square. To undo the square, you have to take the square root. And we'll see you guys later.